What's up guys, and welcome to this video. This is part 2 of our equations of motion, our UVATS videos, series, concept videos, whatever you want to call them. Basically in the first video we went over the general equations, and then we went straight into some examples, and I think we covered 2 examples. Okay, so let's get into example 3 and example 4. Okay, so example 3. Okay, so example 3 is going to be on multiple objects. Okay, so basically 2 or more objects. Okay, so let's say we have 2 cars, car A and B. So we have 2 cars, cars A and B. Car A is traveling at a constant velocity of 25 meters per second, let's say right, when it passes car B, which is stationary. Okay, car B then accelerates uniformly. Okay, so if car A, or let's say rather car A and B meet each other again, seconds later. Okay, so that's the breakdown of the problem. So basically what we have is let's see, we're looking from on top. So we have car A and we have car B. Initially car B is 0, then it accelerates. Okay, car A is initially at 25 meters per second, constant velocity. They both travel, B also starts to move, and 10 seconds later they're both together next to each other. Okay, so that's the breakdown of this question. So let's get into the actual part. So part A, let's say, is calculate how far car... Okay, so calculate the displacement of car A. Okay, so let's see, car A has got a constant velocity. Okay, so acceleration is equal to 0. So for this, quite easy, we use our velocity equals displacement over time. We know the velocity, and we're taking right as being positive. We know the velocity was 25 meters per second, and the time is 10 seconds. Okay, so we can solve for S is equal to 250 meters. Right. Okay, it came out positive, so it has to be right. Okay, question B is calculate the acceleration. Calculate the acceleration of car B. Okay, so here we're going to have to use our UVATS. UVATS. Okay. So let's go for it. Our initial velocity was 0 because it was at rest. The acceleration is unknown. We know that in 10 seconds, we have to be traveling the same, not the same distance. The same distance. So in 10 seconds, these 2 cars travel the same distance. This picture may not be as accurate as it could be. car A and B are next to each other. So the displacement is 250 meters like we calculated before. So what equation can we use? Let's try using S equals ut plus a half at squared. Our unknown is a. That's what we're looking for. So S is 250. Our initial is 0, so that term becomes 0 plus a half times our acceleration times our time squared. So let's plug that into a calculator, and we have an answer of 5 meters per second squared, and it came out positive, so it is right. Okay, and it's what we expect. We expect the car to move right. Okay, then question C is going to be calculate the velocity, final velocity of car B. Okay, so we're looking for V. I'm going to try use an equation that does not use acceleration, if possible. Let's see our equation lists quickly. One that doesn't have acceleration, but displacement we've calculated. So, okay, fine. We're going to have to use one, so we might as well pick the easiest one. So we can use the equation V equals U plus AT. Our initial is 0 plus our acceleration, which is what we calculated as 5, and our time, which was 10 seconds. Okay, so what we're left with is V is equal to 50 meters per second, and it's traveling right. Okay, so that needs to be in red, and that needs to be in blue. Okay, and so that's our final answer. And lastly, question D is draw the velocity time graph and the displacement time graph. Okay, so let us start off with our set of axes. We have, let's see, displacement time and velocity time. Okay, so we have two cars A and B. Let's do the graphs in red. Okay, so my velocity, let's start off with my velocity time graph. Okay, so one of the cars is traveling at a constant velocity of 25 meters per second. 25. Okay, so one of the cars is traveling at a constant velocity of 25 meters per second for the full 10 seconds. So it's going to look like that. That is a straight line graph. Straight. That looks a bit better. There we go, for the full 10 seconds. Okay, so this is car B, if I'm correct. Car A. Car A travels at 10 meters per second, 25 meters per second, so that's car A. And car B starts at 0 and then ends at 50 meters per second, which is what we calculated. Okay, and we know it has a constant velocity, so it looks like that. Okay, so from that we should be able to draw the displacement time graph. Okay, so we know that in 10 seconds it travels 250 meters. So, okay, so we know that's where they both need to end up. They both need to end up there. We know that for the one with constant, for car A, we know that it's a straight line graph because it has constant velocity. So it's going to look like that. For graph B, we can look at the areas. So the area at the start is small, and then the area at the end is very big. So we're going to go from a shallow gradient to a steep gradient. Okay, so shallow gradient, so this is car A. Let me do car B in a different color. So shallow gradient, and then it's going to get steeper and steeper and steeper until the end, which is B. Okay, so that is our graphs. Both of them need to end at the same place. Yeah. Okay, so that's that question done. Okay, then the next question. Okay, this is going to be example 4. Okay, example 4 has to do with stopping distance and reaction times. Okay, so what we have is the following scenario. Okay, so we have two cars, car A and B once again. Okay, so car A is moving at a constant speed of 25 meters per second, right? Okay. At point 1, the driver of car A sees a stationary car B ahead and brakes 0.5 seconds later at point 2. Okay, the acceleration is equal to 5 meters per second squared, and the truck, or the car A, so car A manages to stop 5 meters from uh, 5 meters away from car B at point 3. Okay, so let's draw this thing out, converting everything to words. Okay, let's actually draw it like this. Okay, so we have two cars. Beautiful car, and let's see, it's a nice car. Okay, so A, B. Okay, so we have point 1, we have point 2, and we have point 3. We also know that car B is stationary. Okay, so we have car A and B. Car A is moving at a constant speed. So initially, speed is equal to 25 meters per second. At point 1, the driver sees the stationary car ahead and brakes. So at point 1, we apply the brakes, and it has a difference of 0.5 seconds. Okay, seconds later, at point B, sorry, my handwriting is atrocious, at point 2, okay, the acceleration is equal to 5 meters per second. Okay, so the magnitude of the acceleration, okay, so the car, obviously, to stop before car B needs to be accelerating in the opposite direction. So the acceleration is actually equal to minus 5 meters per second squared. Okay, and we know that that distance there is 5 meters. So this is 0.3, that's 5 meters, and here the acceleration is equal to minus 5 meters per second squared. 5 meters away from car B at 0.3. Okay, so I think we have all the information that we need. Okay, so question 1, or question A, what is the reaction time? Okay, so what is the reaction time? Okay, that's given in the question as 0.5 seconds. Let's see, if we read the question nicely, sees a stationary car ahead and brakes 0.5 seconds later. So this is our reaction time. So reaction time, so the reaction time is equal to 0.5 seconds. Okay, question B is calculate the distance traveled in this time. Okay, so we know that initially this is traveling at a constant velocity, right? So we can use the equation speed or velocity. Velocity equals displacement over time. Our velocity is given as 25 meters per second, and we are taking right as being positive. So 25 meters per second is equal to our displacement over our time, which was 0.5. So solving for displacement is equal to 12,5 meters direction of right. Okay, then question C is calculate how long. So calculate the time taken to come to rest. Okay, so here we're going to need, okay, so here we're concerned about this region right here, how long it takes for that region right there. Okay, let's put the information we've just calculated in. So this distance is 12.5 meters. So we want to know the time taken. So t is what we're looking for in that period right there. Okay, so here we need to use UVATS. Okay, so our initial velocity is 25 meters per second, our final velocity is 0 meters per second, our acceleration is -5, time is the unknown, and displacement is also an unknown. So we're looking for time, so we can use the equation v equals a u plus a t. So we have 0 minus 25 is equal to minus 5t. So time comes out as 5 seconds. Okay, so that's the time taken, that's this time right here. So let's say that's t1. So t reaction and t1. So that's t1. Okay, and I'm sure you guys have guessed it, but then we want to calculate the displacement. Okay, so we can use the equation S is equal to u plus v over 2 times t. So what we have is u was equal to 25 plus 0 divided by 2 times 5, so that's 12.5. 12.5 times 5, so if we plug that into our calculator, we get our displacement there is 62,5 meters. Okay, and then it says calculate how far dE, the distance between the cars, between car A and B. Okay, so this distance we know is 12,5. This distance we calculated right now is 62,5. And we know this distance is 5 meters. So we can say S1 equals 12.5, S2 equals 62.5, and S3 is equal to 5 meters. And S total is made up of those three. So S total is equal to S1 plus S2 plus S3, which is equal to S1, 12.5, 12.5 plus 62.5 plus 5. So if we plug that into our calculators, what do we get? We get 80 meters. Okay, and it's to the right. Or actually you don't need this value there, because we want the distance, which is a scalar. Okay, and lastly, as we, I'm sure, predicted as well, we want the velocity time graph. Okay, so what would the velocity time graph look like? Vt, so we know at time equals 0, at time equals 0, our initial velocity is 25 meters per second. So 25 meters per second. At time, t1 came out as what? 5 seconds. t1 equals 5 seconds. So t total was equal to T reaction plus T1. So T reaction was 0.5 plus T1 is 5 seconds, so our total time is 5.5 seconds. So at 5.5 seconds, the vehicle is at rest. So at 5.5, we're at rest, and we know that at 0.5, we're done traveling at a constant velocity. So for the first 0.5 seconds, we are at a constant velocity. So we have this situation right here. And after that, we are decelerating, we are slowing down at a constant rate, so we're going like that. Okay, and for funsies, let's also do the displacement time graph. Okay, so what does the displacement time graph look like? I'm not going to put values in. Basically, in this region right here, we have constant velocity, so we're going to have a constant gradient like this, something like that. And then after that, what we have is we have a lot of area, so we have steep, and we have small area, so we have shallow. So we're going from steep to shallow, so steep to shallow. There we go, and we know that's at time 5.5, and we know that that distance there is 80 meters. Okay, this isn't drawn to scale. It would probably look something more like this if I was to draw it better, because we know that at time equals 0.5, it has traveled 12.5. So roughly it would look something like this. So it goes like that and slows down. Also probably not great, but you get the general vibe. You need to be going constant here, and then we start off steep and we get shallow. Okay, so yeah, those are the two questions I wanted to cover in this video. In the next video, we might do some questions that have to do with relationships, where we don't use values, but we just use variables. That will probably be next time. So thanks for watching, guys. I hope you found this useful.